So how does the rational tangle dance actually work? Right? How is it possible to find an inverse for a rational tangle in a more efficient way than just using the shoes and socks method to undo every single generator along the way from backwards to forwards? So the secret sauce is the following. What we do is we find two functions. And these are functions in the ordinary sense of the kinds of functions we study in algebra class in high school. And we find two functions that interact with one another in exactly the same ways that the rational tangle group generators interact with one another. Specifically, the rational tangle group generators follow these two cancellation rules. R squared is the identity, right? Every rotation undoes itself if you just do it twice in succession. And also that TR, the combination of a twist followed by a rotation, if I do that thing 3 times, TR, 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 that those all cancel one another out and we get the identity, right? Those were the two cancellation rules that we discovered when we were trying to figure out how to undo rotations and undo twists. And so the secret here is we're going to find two functions, ordinary single variable functions, that behave in the same way under function composition. And here they are. The first function is the add 1 function. T of x equals x plus 1. You give it 10, it gives you 11. You give it negative 1/2, it gives you positive 1/2, right? This is the add 1 function. And the r function, which is the opposite reciprocal function. You give it 3/5, it gives you negative 5/3. You give it negative 5/3, it gives you back 3/5. So it's probably obvious to ask this question, but which one of these do you think represents a twist and which one do you think represents a rotation? So of course, T is the twist, R is the rotation, but why? So what we need to figure out is why is it that these functions have the same algebraic structure, are capable of encoding the same algebraic behavior as the rational tangle group generators are, right? After all, these are just functions. We understand what their graphs are, right? Here's the add 1 function graph. Here is the opposite reciprocal graph. And so what happens when we start to compose these with one another, remember, function composition means feed the output of one function into the input of the next function, is that we build more and more complicated rational functions. For example, if I have the rational tangle TTR, TRRT, right? So 2 twists followed by a rotation, another twist, 2 rotations, and then a twist. The function that I would get that represents that would be the result of taking and applying first the add 1 function, the T function, twice, and then I would apply the rotation function to that result. Then I would apply the twist function to that result. Then I would apply the rotation function twice to that result, and then the twist function one more time to that result. And so I would get the function composition, T happens, then T happens, then R happens, then T happens, then R, then R, then T. And so the function composition that I get looks backwards from the rational tangle word that I wrote down, just because that's how function composition works, right? In the composition F circle G, it's the G function that happens first to x, and then the f function happens to the result of g of x, right? If you teach algebra 2 or pre-calculus, you know how much your students love f of g of h of k of x kind of problems, right? Everyone hates them, and yet composition of functions is probably the most primal form of algebraic structure. And this is one of those kinds of examples. And so in this example, if I do all of that composition, I get unsimplified, I get this sort of nasty looking function, minus 1 over minus 1 over minus 1 over x plus 2 plus 1, all plus 1. If, again, we assign a problem to our, AP calculus students, simplify this into a single rational expression, they can simplify it to 2x plus 3 over x plus 2. But the point is how it was constructed. The point is not so much what the function was. So I have a widget here. It's in our textbook page. We can spell out a rational tangle word using T's and R's, and this widget is going to show me a graph and a formula for the function which results from that composition of our twist function and our rotation function. So coming back to this example, TTR, TRRT, I would just click T, T, right? So if I apply a twist function twice, I get the function that adds 2 instead of adding 1. R, so now I'm taking the opposite reciprocal of the x plus 2. T, RR, T. And so ultimately, at the end of the day, here is a graph of the function that's represented by that rational tangle word. The other thing that's being labeled on here is it's just labeling the y-intercept of this function. The y-intercept is 3/2. So we'll just do these verifications together, and then I'll give you a 5 or 10 minute thing to talk about with your group before we wrap up today. The question is, how can we be sure that these functions do the same things that the rational tangle generators T and R do? How can they encode the same algebraic structure? And to verify that, we have to kind of verify two things. We need to verify that my rotation function is its own inverse, and also to verify that the composition T followed by R, if I do that thing 3 times, TR, 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 in other words, R of T of R of T of R of T of X, that should all cancel out and give me the identity element in the group of functions. And the identity function is the function that we saw here in the beginning, g of x equals x. Right? The identity function is the function that does nothing. Whatever input you give it, it gives you that same thing as the output. Right? That is the identity element in any group of functions under composition, because anytime I compose with this function, it's the same as not composing with it at all. Right? So this is my identity, and so that's how I know that I've canceled my thing out. So why is R composed with R the identity? We can check using this graph. Let's say I start with some tangle, whatever. Sort of put whatever word I want here. So here's a tangle. If I do R once, I get clearly a different function. But if I then do R a second time, I'm back to the function that I just had. Why does this make sense? Well, because R is just an opposite reciprocal. And if I take the opposite reciprocal of an opposite reciprocal, we can just do this using the formula. Right? What is R of x? Well, that's just R of the opposite reciprocal of x, because that was the definition of my R function. And R of minus 1 over x is minus 1 over x. But then, you know, you do your complex function or complex fraction thing, multiply the numerator and denominator by x and by negative 1. So multiply by negative x on the numerator and in the denominator. In my numerator, I get x. In my denominator, I get 1. And so when I compose the R function with itself, I end up getting whatever input that I gave that function, I get that same input back as output. So R composed with R is the identity function, e of x equals x. And so that's how the rotation function can do the same thing that the rotation of rational tangles did, right? It undoes itself after just a single iteration. It is its own inverse. The other one is a little bit more interesting. So TR to the third power is equal to the identity in the rational tangle group, right? And so what's going to represent TR? TR is going to be T composed with R. T happens first and R happens second. So this really should be R composed with T. So let's figure out what R composed with T is. This is R of T of x. Well, T of x is x plus 1. And so R of that is minus 1 over x plus 1. So this is the function, minus 1 over x plus 1, that represents TR. Here is its graph, using my little widget over here. So this is what my TR function looks like. So now my question is, how do I know that this thing done 3 times is going to give me the identity back? Let's check on that. So I'm going to call this function f of x. And so my question is, what is f of x? This is a threefold composition of this function with itself, because composition of functions is the operation that we're relating our rational tangle operation to. All right, so this is going to be f of minus 1 over x plus 1. Now here comes the really fun part. F of minus 1 over x plus 1 is minus 1 over x plus 1 plus 1, right? And then f of that, it gets even more fun. It's minus 1 over x plus 1 plus 1 plus 1. Yeah, I think that's it, right? So this is some nasty looking thing. And if I want to understand what this thing is, I should probably start by, I don't know, multiplying this denominator by x plus 1 to clear it out, which means multiplying this numerator by x plus 1. So I'll get minus the quantity x plus 1 on top. And then downstairs, I'm going to get -1 plus x plus 1. So that's actually just going to be x. So our fraction is slightly less complex. Then to rationalize, not rationalize, but simplify this big denominator here, I'll multiply it all by x to clear out that denominator. So my new numerator here is going to be minus x. Really thrilling algebra to end the day here. It's going to give me minus the quantity x plus 1 plus x. And sure enough, when I distribute this minus into the x plus 1, it's going to be minus x minus 1, and then add x. This is going to simplify to minus 1. Minus x over minus 1. Oh, look, that's just x. Which is what we were hoping for, right? It tells me that r of t composed with itself 3 times gives me the identity function. So these rational functions are behaving the same way that the rational tangle generators did. TR, TR, TR gave me my identity function back again. So anything that our rational tangles can do, these rational functions can mimic. The one sticky part of that, and one of your groups already noticed this today, is that there is actually one rational tangle that these functions can't tell is not trivial. Sorry, it's the other way around. The functions think it's not trivial, but the rational tangles think it is trivial. That's the tangle TRT. So if I just do TRT as in terms of these functions, I get something that's not the identity. I get x over x plus 1. But if you actually compose TRT as a rational tangle with your strings, you'll find out that you end up actually getting a trivial rational tangle. This is activity number 9, so you do a little bit of investigation there. So that's the one drawback to using these functions. And the way we can resolve that drawback is to notice that the thing that's the same about TRT and about the original rational function that's the identity, the thing that's the same is the y-intercept. And the cool theorem, and this is the thing that powers the whole enterprise, is that the y-intercepts of these functions are actually in one-to-one correspondence with the rational tangles. Every rational tangle corresponds to a single rational number, which is the y-intercept of its associated function. And vice versa, every rational number is the y-intercept of one of these functions that corresponds uniquely to some rational tangle. And that number, that rational number that we get in this process, is called the fraction, or the tangle fraction of a rational tangle. So, just to wrap things up for today, suppose I have a rational tangle, like let's look at activity number 10 here. Let's take this tangle over here. Yeah, let's take the first one here. T squared r, t cubed rt. We can find the fraction of this rational tangle just by forming that composition of these functions, right, and then finding the y-intercept of that composition. So t squared r, t cubed rt. I'm going to refresh the page to reset this app here. So t squared r. Notice every time I hit t, my y-intercept is going up by 1. Every time I hit r, my y-intercept is going to its opposite reciprocal. This makes perfect sense, right? Because that's what those functions are doing to their inputs. So t squared r, t cubed, so I add 3 more, r, opposite reciprocal, t. So the fraction of that rational tangle is the rational number 3/5, because that composition of these functions gives me a rational function whose y-intercept is 3/5. Now, here's what makes the rational tangle dance work. I can untangle this tangle by focusing on this fraction instead and asking, how do I get this fraction to be back to 0? How do I turn 3/5 back into 0 through a process of adding 1 and taking opposite reciprocals? Well, here's a way that I can do it. I'll start with a reciprocal, opposite reciprocal. So 3/5 becomes -5/3. Then I'll start twisting. Maybe I'll do it twice. Now that I have a positive number again, 1/3, I'll take a opposite reciprocal again. That's going to give me -3. Zoom out here. -3, right? And now that I have at -3, hey, that's a whole number. That's an integer. And so all I need to do to get to 0 is add 3 twists. And now I have a rational tangle. This is going to be a rational tangle whose fraction is equal to 0. And so it's going to be isotopic to the tangle TRT, which had the same function as its representative and which was a trivial rational tangle, an untangled rational tangle. So we can untangle a rational tangle just by figuring out what was its fraction, and then figuring out what steps of adding 1 and taking opposite reciprocals are going to take that fraction back to 0. because once we've gotten back to 0, we have gotten back to an empty rational tangle. So my closing remark on this is that the fraction of a rational tangle is what's called an invariant. And invariants are going to consume us next week and the week after. Because what an invariant means is it's something that has the ability to tell the difference between two different objects. So if I have two rational tangles that have different fractions, then they must have been different rational tangles to begin with, right? The rational tangle associated with the rational number -6 is a different tangle than the one associated with the rational number 1/5, right? If the rational numbers are different, then the tangles are different. Conversely, if the rational numbers are the same, then the tangles must have been the same. In that sense, the tangle of the fraction of a rational tangle is called a complete invariance. It can both tell the difference between different tangles, and it can also tell when two rational tangles are the same. When it comes to knots, which we're going to dig into starting next week, some of our invariants, actually most of our invariants, are not going to be quite that nice. They're going to have the ability to tell the difference between different knots, but they can't always tell when two knots are the same. So when something can tell the difference and tell sameness, we call that a complete invariant. And rational tangles have these rational numbers, their fractions, as a complete invariant. That's why rational tangles are awesome. But with knots, we're not so lucky. In order to build a complete invariant for knots, we need a much more sophisticated, much higher firepower algebraic structure. That is going to be our goal that we're working towards for the next 2 weeks.